Hi, today's video is going to be Lab 15, which is reaction rates in equilibrium. It's kind of a fun one. There's a lot of visual stuff, but not a lot of calculations. The first part of it, I'll just talk about, but what you've done is taken a small amount of ammonium nitrate and put it in a test tube of water, and then second we put a little bit of calcium chloride in a test tube of water and see what happens. So typically what happens is we've got a room temperature start. So if we say maybe we're 25 degrees Celsius, and we monitor with a thermometer, but your hand is almost a better tool for this. With the ammonium nitrate, we typically drop a couple of degrees, 22 or so. Say it went to 22.5 degrees, and the calcium chloride typically heats up. All right, so we had the ammonium nitrate cool off, again, cold to the touch. The calcium chloride, it's a little warmer to the touch. We can calculate our temperature change, just our temperature change we write as delta T, and that's going to be final temperature minus initial temperature. So again, pretty straightforward to calculate. Endothermic or exothermic, that's based on whether heat went in or out of the system, and away we go. All right. The next part I'm going to try to do as a visual here. So what I've got is 3 test tubes that have, from left to right, 1, 2, and 3 molar hydrochloric acid. So that's going to line up with these guys. So get ready to start your stopwatches here. I'm going to drop a small piece of magnesium in each one of these and just see what happens. So there's 1, there's 2, there's 3, and I hope I don't make too much of a mess when I do this. It's a very vigorous reaction. Oops. This is the same reaction of the magnesium hydrochloric acid lab where we did the gas laws, collected the hydrogen. So it looks like the 3 molar is done. The 2 molar is done. One molar still going. And 1 molar is done. All right, so note those times. Washes the hydrochloric acid off seals. All right, sorry for the break there. I had to go wash my hands. All right, so again, we noted the time for each one of those. So go ahead and again watch it again if you didn't note those. Exothermic or endothermic, they're all exothermic. And then of course the reaction rate, the shorter the time, the faster the reaction. Maybe we'll talk about this in a separate video lecture. All right, another sort of fun part is part C, where we're looking at the reaction of copper hydroxide, which is a solid, dissolving to give us copper 2+ ions and hydroxide ions. If you've read up on equilibria here, we might be able to push the reaction to the right if we can get rid of one of these ions that are formed on the right, or push it to the left if we were to add these. So the first thing to do with this is that we need to make a copper hydroxide solution. So this right here is going to be the copper sulfate, and what we're going to do is add sodium hydroxide to it to form a little bit of the copper hydroxide precipitate. So if we notice, as I add hydroxide, I'm getting this solid mucky stuff forming. Shake it up and I have this sort of dark blue material, and that opaque material here is the copper hydroxide. All right, then I need to put this into 3 clean containers. All right, so here's our 3 test tubes of the copper hydroxide in equilibrium. And what's important to note is that it's both a little bit blue in color, which is the copper ions in water, and also that it's a little bit cloudy, which says that we have a suspension of the copper hydroxide solid. All right, so to these 3 test tubes, I'll add the sodium hydroxide to the first one. And we should see more formation of the solid. We'll add ammonia to the second one. Come back to that, and we'll add hydrochloric acid to the third one. All right, so we saw an obvious change in the color. The copper hydroxide test tube got bluer, it looks like, but what's important here is that it's more cloudy. So if that's really obvious in the video here, but it's got more of that opacity of the solid. The ammonia one got much brighter blue, but the difference here is that this is actually fairly clear. A little bit of cloudiness still, but it's got less of the copper hydroxide. And we added acid. There's the faint blue of some of the copper ions, but the solution is definitely very clear. I'm going to add a little more ammonia to this middle one and see if we can get that to really lose the opacity. Yeah. Oh, medium. All right. So what we have then is the initial appearance was cloudy blue for all 3 of them. And the change that we should have seen for test tube 1 was an increase in cloudiness. Test tube 2 was a darker blue, but a clearing of the solution. And in test tube 3, the color got fainter and the solution got clearer. And so what that tells us is that in number 1, we pushed the reaction to the left, forming copper hydroxide. In number 2, we pulled the reaction to the right, forming less of the copper hydroxide. The copper here doesn't exist as copper 2 anymore. When we have the ammonia, we actually have this complex of copper ion having, turns out there's 4, but 4 ammonias around it. And this complex ion is an intense blue, but it's soluble, so it doesn't have that particulate that's creating the cloudiness. And then in test tube 3, we added HCl, and that acid chewed up the hydroxide, and that pulled the reaction across and resulted in just copper ions and getting rid of the copper hydroxide that was there. All right. should we worry about here? Question 7 is a good one for something called Le Chatelier's principle. That's a good one to be able to qualitatively predict what happens in a reaction. In essence, Le Chatelier's principle is anything that you do to a reaction, the reaction will pick a direction that undoes what you did. So if you add heat, the question is, well, how can the reaction get rid of the heat? And it would use it as a reactant and pull the reaction to the right. If you add CO, then that causes the reaction to want to get rid of CO, go to the left, etc. So it's a good one to look at. And question, or rather part D, let's just run through what happens. But we set up an initial solution that has the iron 3 plus thiocyanate, and that forms FeSCN 2 plus. And all of these are soluble. The iron 3 plus is very pale in color. The thiocyanate is colorless. And the iron thiocyanate is very intense, almost like tomato juice. So these initial colors, we might just say red, red, red the whole way down. So those are all the same, and that's what's key. And then the final color is after we've done anything. In step 1, we just add a little bit of water, so nothing really happens. If you had really good eyes, you might see a slightly less intense solution, less intense color, but it's a pretty subtle difference. All right, when we add iron, we go from red to dark red. So we'll go ahead and write that. Red for all of these, dark red here. When we add thiocyanate, dark red. When we add chloride, the solution becomes less red. So it's telling us that we're getting rid of the thiocyanate. When we heat things up, the reaction becomes less intense, so less red. When we cool it down, it becomes darker red. So again, repeating those, no change, darker, darker, lighter, lighter, darker. And then what we have to do is say, well, what does that mean in terms of the ions that are increasing or decreasing? Really what we care about is the iron thiocyanate. If we add iron, clearly the iron increases, but that's just because we added it. What's really happening is the reaction's getting pushed to the right, which would decrease the thiocyanate and increase the iron thiocyanate. So probably in this table, the first thing to really do is ask ourselves, which way did the equilibrium get shifted? And if the color change resulted in something being darker, then the equilibrium shifted to the right or towards the FeSCN 2 plus. We always want to be very clear that we're referencing a specific reaction. So again, first step is decide which way the reaction went. That's based on the color change, and then work backward and say, okay, what decreased and what increased. And then problem 9 is, or question 9 is just redoing basically those same things. So give that a shot, and there's no calculations, so there you go.